Hope you have been enjoying as much as I have. And now we have the third lecture by Professor Andrea Liu. Go ahead, Andrea.
Okay, so you must all be rather tired after all these lectures. Um, but all right, so I'm going to be talking today about how we're harnessing concepts that come from machine learning to do inverse design. Um, and we're interested in several systems that I have pictures of down here. This is a protein that has a function called allostery, which I will tell you about, where when a molecule binds over here, it enables, no, it binds over here, it changes the conformation of the protein so that a target molecule can bind over there. This is a network that was, this is actually a picture of a real network that was made in the lab that was prepared in such a way that has a negative Poisson ratio. So when you stretch it this way, it'll um, elongate in the orthogonal direction, which is unusual, not like a rubber band. This is the brain vasculature. So it's the blood vessels of network of blood vessels in the brain. Sorry, it's early for me too. Where that delivers blood flow to the brain. Um, and this is a network that our collaborators, Sam Dillevue and Doug Durian, made in the lab that learns. They can learn how to do machine learning tests. So that's what I'm going to tell you about today. Oh, yes. And before I forget, I've been meaning to show this. We now have the Center for Soft and Living Matter at Penn. So, okay, you guys, none of you are undergraduates, but come and join us. Um, there are over 60 of us from more than 10 departments, about 12 departments across campus, arts and sciences, engineering, and the medical school. And it's an amazing group of people. You can just see a few of the awards that have been made to the faculty in the center since we started in the January 2021. We're having new space renovated in the building, so so you should come and join us. Okay, so or come and visit. All right, so the first thing I mentioned was the Poisson ratio. Okay, so suppose we want to design a material with a specified Poisson ratio. Now, most materials have positive Poisson ratio. So what is it? So D here is the dimensionality, B is the bulk modulus, and G is the shear modulus. Okay, so the Poisson ratio just depends on the ratio of the shear modulus to the bulk modulus and the dimensionality. Okay, and in 3 dimensions, it ranges from -1 to a half. Now, positive Poisson ratio is the normal situation, okay, where the ratio of the shear to bulk modulus is smaller than 1 over 1 over smaller than a half. Let's see. Yeah, I guess it's 1 over d minus 1. Anyway, so when the ratio of the shear to bulk modulus is small enough, I'm blanking on maybe it's d over d minus 1. The Poisson ratio is positive. And what happens then is that, right, it's like a rubber band. You stretch it this way, it shrinks in the other 2 directions. Now, cork is an amazing material, and it's so useful to us because it has a Poisson ratio that's very close to 0. So when you squish it in the bottle, it doesn't change its dimensions in the orthogonal directions. But there are materials like tendons, in fact, that are auxetic. They have a negative Poisson ratio. So when I stretch in this direction, it will stretch in that, it will elongate in the other directions. Oh, here it is, it's d over 2. When negative when g over b is greater than d over 2. All right, so we got into this when this is Sid Nagel and I started thinking about this several years ago. And we started thinking about, well, you know, in jam packings, we know that the ratio of the shear to bulk modulus is very tunable. But while it's much more tunable than in most systems, still it's only tunable over the positive range. But we started thinking about it and thinking what made it tunable. So let me tell you a little bit about jamming. So the way we normally talk about jamming is that you have spheres, or in this 2 dimensions, disks, okay, that have a repulsive energy. So just say it's a repulsive harmonic energy, so that there's like, as soon as they overlap, it's like there's a spring pushing them apart, okay? But no interaction if they don't overlap. So only the repulsive half of the spring. And then what you do is you start with some configuration and you minimize the energy because you want to look at the system as 0 temperature. Okay, and if you're at a low enough density, none of the particles overlap. But if you're at too high of a density, you get unavoidable overlaps between the particles. And this red network is the network of repulsive forces in the system that are pushing the particles apart. Okay, so it's a network of contacts. So, but a different way to think about this is as a constraint satisfaction problem. So the idea is you apply constraints and you say, I want to satisfy the constraint that I don't want any overlaps between my particles. And in order to enforce this constraint, what you do is you construct a cost function. You say, I have to pay if there are overlaps, okay? And if you pay a harmonic cost, okay, you can call that the energy, that's what I pay. And then the idea is I'm going to adjust my degrees of freedom, which in this case are the positions of the particles. I'm free to adjust the positions of the particles to satisfy this constraint of no overlap between spheres. Okay, so what does this thing look like? Well, at low density, right? At low enough density, the energy has this big flat global minimum, and no matter where you start, it's really easy to find a state where none of them are overlapping. As I increase the density, it gets harder and harder, and then at some point, you can't satisfy all the constraints, and that's when you're jammed. Okay, that's the jamming transition, when you go from here to here. All right, so what happens to the ratio of the shear to bulk modulus when you do that? Well, it's instructive to compare to the perfect crystal, which for this system, the lowest energy state is the FCC crystal. Okay, so if I have the crystal and I have the particles overlapping, so they're not happy, okay, they're pushing each other apart. I have the particles overlapping. What is the ratio of the shear to bulk modulus? It's some constant. And as I decrease the ratio, okay, it doesn't change at all. Okay, the ratio of the shear to bulk modulus remains absolutely constant until you reach the point where they're no longer touching. And then if I decrease the density below that, you know, the thing will fall apart. Okay, so as I go to 0 pressure, as long as there's any overlap, the ratio of the shear to bulk modulus is absolutely constant. But if you do the disordered case, if you look at the jam system, so you start with these disordered configurations and look at where they jam, okay? What you see as you decrease the pressure is that the ratio of the shear to bulk modulus drops as a power law, okay? And it goes to 0 at the transition, marking basically a smooth transition to the liquid, the fluid state, instead of a first order jump as you get for the crystal. So you can see that the ratio of the shear to bulk modulus is much, much more tunable for the jam solid than for the crystal. So that's what we knew, and that's what we started with, okay? And now if you think about it, let's think about it like this. I'm going to now take away all the forces. So I just consider the network of contacts. So I take my springs and I adjust them so that their equilibrium lengths are just the length of the spring, so that I get rid of all the forces. Okay. And now what I do is I put a node of my spring network at the center of every sphere, and I put a spring between every two spheres that are overlapping. Okay. So I can look at this equivalent spring network. Now, if I keep the forces on the springs, if I don't adjust the equilibrium lengths, it turns out that these two systems are equivalent in linear response. And if I take away the forces, okay, they're not equivalent, but they show the same scaling at the ratio of the shear to bulk modulus. So I'm going to stick with that. Just to understand the scaling of the ratio of the shear to bulk modulus, I'm going to stick to that unstressed case. Okay, so now if we now imagine what happens as we lower the pressure or the density of the system towards jamming, what happens is that, some of the particles that were overlapping are now not overlapping. So what I'm doing is I'm losing springs. I'm removing springs from the system. So lowering the pressure is like removing edges from this network. So now let me think about what happens when I remove an edge. Okay, I can take away this bond, and I can look at the change in the bulk modulus when I take away that bond and the change in the shear modulus. So, and the amazing thing that we find is that the change of the bulk modulus is completely uncorrelated with the change in the shear modulus for these disordered networks. So now let me look at the distributions. Let me do this for every single spring in the network and look at the distributions of these. What do they look like? Well, for the crystal, we know what they look like, right? We should get delta functions, and it depends on the crystal structure where these delta functions are, okay? And so that's what it would look like. And if you add disorder, what you would expect is that these delta functions would just fuzz out, okay? They would get broader. That's not what happens. It looks like this. Okay, you get a distribution that is power law over much of its range and then has an exponential cutoff. In fact, it is this form, and we can derive this analytically. I'm not going to go into that. But the interesting thing is that the distribution, after you've done a little pruning, for the bulk modulus is the same as it is for the shear modulus. And all we have to do, and it's the same at every stage of pruning, all we have to do is divide the change in the bulk modulus by the average over all of the bonds that change in bulk modulus, and the distributions collapse no matter how far we are into the tuning process, okay? And no matter whether we're looking at the bulk or shear modulus, it is the same distribution. And the key is it's a quite broad distribution. It's cut off at the high end, and it goes continuously all the way to zero. So now, okay, we know something. We know, and this is beautiful work that was done by Dr. Ellenbrook when he was a graduate student with Martin van Hecke and Wim van Saarloos in Leiden. Let me introduce what I'm going to call little edge demons, okay? I'm going to go in there, and I'm going to say pruning edge demons. I can just go in there, and I can cut whichever bond I want. Okay, and what we knew from this paper was that if you prune completely randomly, you get that the shear to bulk modulus is a constant. It's like it is for the crystal. You completely lose that jamming behavior where the ratio of G over B goes to zero as you prune it. Okay, instead it remains constant. Okay, so then we thought, well, let's have fun. Okay, let's prune the bond, selectively prune the bond that changes the bulk modulus the most. If we do that, what we're doing is for the bulk modulus, we're moving something at the top edge of the distribution. But for the shear modulus, right, it's the change in the shear modulus is totally uncorrelated with change in the bulk modulus. So it's as if I'm removing a bond at random. So it's as if I'm removing something from the mean. So the drop in the bulk modulus is going to be bigger than the drop in the shear modulus. And if I just do this over and over again, always choosing the bond that changes the bulk modulus the most, the ratio of the shear to bulk modulus shoots up incredibly rapidly. With the power law, if you want to fit it to a power law, we understand that, how we understand this behavior as well. That's in this paper here by Daniel Hexner. Yeah, the power law is like 9 or 10. It's huge. It just shoots up, okay? And I can get a 12 orders of magnitude change in the ratio of the shear modulus, pruning about 1% of the bonds. And very, very rapidly, okay, I get into the regime where the shear to bulk modulus is bigger than 3/2 in 3 dimensions, okay? And that means my Poisson ratio is negative once I'm in this range. Okay, and it goes to its most negative value when G over B goes to infinity. So it's essentially -1 here. Okay, so it's perfectly, it's perfectly auxetic at that point. Okay, maximum negative Poisson ratio. So if we think about what we're doing, what we're doing is we're doing gradient descent on the bulk modulus, right? When we're taking away the thing that changes the bulk modulus the most, we're taking the step, right, that we're doing gradient descent on the bulk modulus. And what are our learning degrees of freedom here? What are we doing here? We're introducing these degrees of freedom on the bonds that we're saying they can either be there or I can take them away. That's it. I'm introducing a degree of freedom. That's what my pruning daemon is doing. Okay. And then we thought, oh, we could do anything we wanted. It doesn't have to just be we prune the bond. We could take the bond here and we could stuff it there. Mathieu of the arts group has done that. Okay. We can change the stiffnesses of the edges. We can change the equilibrium lengths of the edges. We can tune any mechanical property we want that can be written as the sum over edges. Okay, that's how that asterisk is. Okay, all we have to do is to construct the right cost function, which in this case is the bulk modulus, and then do gradient descent on it. Okay, so then we started getting ambitious. We said, okay, can we learn allostery? Okay, so I told you a little bit about allostery. Here's my protein. Here's some molecule that wants to be chemically modified by it. Let's suppose this is an enzyme. A lot of signaling proteins work this way too. So right now, this molecule can't bind. Is there a question? No?
No, Andrea.
Okay. Right now, this molecule can't bind, but when this other molecule over here binds, that changes the conformation of the protein so that now this can bind. Okay. So that's allostery, the localized strain over here in response to a strain applied here. Okay, so I apply source strain, I get a desired target strain, and the source and the target can be far apart from each other. Okay, and you think, oh, I am an expert now on disordered elastic systems, and I know that elasticity is long ranged, right? But in fact, deformation decays quite rapidly with distance, and for these systems, if you estimate it, given their moduli, you would expect the target strain here to be about 2 to 3 orders of magnitude smaller than it is here. But as you can see, for these systems, in order for something to bind, when something binds here, okay, the change at the target has to be of the same order of magnitude as the source strain, okay? This has to be as big as this, and that is special. That's not normal. Okay, so here's the brain vasculature. Here's the other system I told you about. So it turns out the brain, right, 2% of our body mass uses a huge fraction of our oxygen. Is there an echo, or is that just for me? It's okay for you guys? No problem with
It's
the
okay
sound?
for us. I don't know.
Okay, good. All right, no problem then. So the brain, right? What's happening in the brain is that there's a large influx of blood through the arteries. So there's a large pressure drop across the arteries. Okay, so that's the source. Okay. Now, what the brain does, the reason why the brain uses so much oxygen is that when the brain is active, it needs more oxygen. Okay. And so different parts of the brain are active depending on what you're doing. So right now I'm talking, so my speech cortex needs more oxygen, and therefore I have what my brain vascular system is doing is that some blood vessels are shrinking and others are dilating to direct blood flow to my speech cortex. Okay. Now, if I stopped talking and started jumping up and down, you would think I'm crazy. Okay. But my brain would just adjust and send blood flow, extra blood flow to my motor cortex. Okay. So it's sending blood flow to different places on demand. And what it's doing is it's changing the conductance of edges of this flow network to do it. So this is just like the allostery problem, okay? Except it's flow allostery. Okay, so how do we do this? And I showed you last time, right? That the flow, I think I showed you, flow mechanical networks are basically the same problem. Flow networks, you have to obey Kirchhoff's law. So if you have a flow network here, like imagine this is a network of pipes, okay, of different conductances. And I have some input pressure drop here and output pressure drop here. In this system, right, it has to minimize the power. And so I have to satisfy Kirchhoff's law at every node. Okay, no net current at every node. In the mechanical network and network of springs, I apply a displacement here. Okay, I apply strain here. I want to give an output strain here. Okay, the system has to minimize the energy. And so the node positions are going to adjust. Those are the degrees of freedom that are going to adjust so that there's no net force on every node. Okay, so this thing of no net force on every node is very similar to Kirchhoff's law, no net current at every node. And the equations are almost the same. It's just that flow networks are simple sort of 1D version of mechanical networks. So we might as well do the two problems at the same time. Okay, so what we want to do is design these networks to have that allostery the way I describe it. Source here, target there. Okay. So, but the way we're going to do it is not to start with a folded protein, for example, and turn it into a spring network. There is a very happy community of people who do that for a living. Okay, they take folded proteins and they turn them into spring networks. Okay, and then they study the properties of the proteins by studying these spring networks. Okay, we're not going to do that. That's not enough examples for us. What we want, right, is we want to take any network that we start with and we want to design it, okay, by changing the spring constants or the equilibrium lengths or pruning springs or taking a spring away here and putting it in here, okay, doing something like that. We want to design these things to have allostery, okay? And so we're going to start with an ensemble of networks. And, you know, because we were working on jamming for so many years, we had all these jammed configurations lying around. We just turned them into spring networks. And so we had an ensemble of spring networks. Okay, so that's the networks we started with, was for these jam networks. Okay, and the idea is we would take each one and we would tune the same allosteric function into each one. Okay. And so now the question is, how do we do that? Okay. So when you think about it, right, usually what we do is we start with a system And then we say, okay, suppose I apply a target, a strain here at the source. What's the strain over there? Or suppose I apply a pressure drop at the artery, what's the pressure drop over here, the speech cortex or wherever it is. I have no idea where the speech cortex is. Okay. That's the forwards problem. That's the problem that we're used to, that we know how to solve. Okay. But that's not the problem we want to solve. What we want to solve is the inverse problem. What we want to know is what network is going to give me the desired target strain or the desired pressure drop. Okay? And the way people usually solve it is by solving the forwards problem exhaustively, mapping it all out, and then interpolating the results to figure out what network would do it. But that's extremely inefficient and a bad way of doing it. Is there a better way? And this is where, the work that we did on softness, teaching us about machine learning, was so helpful, because of course, the whole idea of training a neural network to learn, for example, the difference between cats and dogs, that everybody always chooses cats and dogs. I don't know why. The whole idea is to solve an inverse problem. That's exactly what the neural network is doing, right? Because you feed it the pictures and you want to train the neural network to give you the right answer. Okay? So what are you doing when you train a neural network? Well, you got the inputs, the images, okay? And then you at the other end, you have the output. You want, for example, this to be 1 for a dog and 0 for a cat, and you want this to say 1 for a cat and 0 for a dog, okay? So that's what you want. And how do you do it? It's exactly the way I described jamming as a constraint satisfaction problem. You solve it as a constraint satisfaction problem. So you construct a learning cost function where you pay a price. If your output here and output here and the output here are different from what you want them to be. Okay, so you just take that difference, you square it, and you sum over your outputs. And now you do gradient descent. You minimize this thing with respect to the node weights, okay, of your network. And that's called backpropagation. So you do gradient descent on learning cost function. There's a clever way to do it called backpropagation with respect to the learning degrees of freedom. Okay, and then you keep doing this. So you take a step, you adjust your node weights, you look at your outputs again, evaluate your learning cost function, calculate the gradient, go back and adjust again. Okay, each time you have to solve the forwards problem with the new weights, look at the learning cost function, and then do backpropagation to take a step to adjust your weights, forwards, backwards, forwards, backwards, okay, until your learning function cost function is 0. So that's how you train a neural network. So if we want to do that in our systems, we can just do exactly the same thing. We construct a learning cost function that says, I'm going to pay a price if the strain at the target is different from the desired strain at the target. I just pay a price. That's it. And then I introduce learning degrees of freedom, which, as I said, could be the spring stiffnesses or the equilibrium lengths, or the presence or absence of a bond. All of these things could be learning degrees of freedom. But I can't forget that this is a physical system. Unlike the artificial neural network, this is a real system. And so at the same time, physics says I have to minimize the physical cost function, which if I'm at 0 temperature is the elastic energy. Okay, and I have to minimize this with respect to physical degrees of freedom, which are the node positions. So the forwards calculation here is I minimize the physical cost function with respect to the physical degrees of freedom, as required by the physics. And then I evaluate my learning cost function. And then I do something that's the equivalent of backpropagation. I use gradient descent to minimize the learning cost function with respect to the learning degrees of freedom. But at each step of back propagation, I have to be in equilibrium according to the physical cost function. I have to be at the lowest elastic energy. I have to minimize that. So I always have to respect physics as I do this. Okay. But as long as you do that, you can then follow this and you can do it. And I showed you last time that it works. Now we can do this for flow allostery as well, right? We just say, I want my target pressure drop here to be the same as the desired pressure drop. My learning degrees of freedom are the conductances of the edges, just like in the brain vasculature. Okay, my physical cost function, which has to be satisfied, is that the power dissipated must be minimized, and the edge currents or the node pressures are going to adjust to minimize that. Okay, and then it's the same thing. Two different cost functions and two different sets of degrees of freedom to minimize with them with respect to. So that's the idea. You can do this for anything. In other words, suppose I want to do this at non-zero temperature. No problem. I just minimize the free energy instead of the energy. And I can do inverse design at non-zero temperature. And in fact, Purbet Chatterjee, who's a postdoc working with Sid Nagel and me, has shown that she can design systems to have negative Poisson ratio at non-zero temperature using this approach. Okay, it works. No problem. Okay, and Jovana Andreevich is doing that with allostery. Okay, so right now. So I showed you these animations last time. It does work. There's the strain at the target in response to a strain of 1 at the source. It started out at around 10 to the minus 3, 5 times to the minus 3. As I tune, it goes, the strain target goes up and up until it reaches the desired value of 1. Here again, the pressure drop over here generically started, around 10 minus 3. Here's the target, the source pressure drop, which, by the way, I could take this whole language and electrical networks of resistors. It's exactly the same language. This would be a voltage drop of 1 and a voltage drop here, but I would still have edge currents and edge conductances. The math is identical in that case, so the two problems are the same. And as I tune this, the edge conductances here, right, the pressure drop at the target just keeps increasing until it reaches the desired value of 0.2. I think I showed that to you last time.
Hi, Andrea. Can I ask a question?
Yeah.
So do you constrain, for instance, the number of nodes or anything like that to be fixed? Or what other kinds of constraints? Because I can imagine the system
so
become very
so
simple.
far, we have fixed the number of nodes. Okay. And we just can take bonds away or keep them, or take bonds away, put them in someplace else. Okay. But we have not played around with nodes. But in fact, it's really interesting to play around with nodes because networks like the actin myosin cortex, they're cross-linking proteins, okay, that will come off if the stress on the node is too high. They will detach. And so they are changing their network topology. Okay. And so I have a postdoc, Marco Galvani Cunha, who is working with John Crocker and me, and he is actually looking at what is the effect of that changing crosslinks. Okay, so letting nodes appear and disappear. What can we train with that as a degree of freedom?
Very interesting.
So yeah, that's a really interesting question, and the answer is yes, you can.
Thank you.
Okay, they're extremely adaptable to allostery. So for one thing, if I wanted the response of the target to be the same as the source, so that's 1 here, okay, the success rate is almost 100%. Okay. Not only that, it turns out that for a network of about 1,000 edges in 3D, I have to remove on average about 5 bonds in order to get a response of order 1. Okay. I think this is 2D, the fracture remove edges. It depends on the size of the system because there's a scaling. It scales like the linear size of the system. But in this case, it's about 1.5% of the bonds to get the target response. Okay, so we can get a strain here that's the same as the source strain with essentially 100% success, pruning a very tiny fraction of the bonds. Okay, it's really, really easy to get allosteric. And when we do that, right, we can take the design networks that we get by doing gradient descent on the computer, and we can laser cut them. This was done by Nidhi Pashin in Sid Nagel's lab. So she laser cut these networks. You see that she made them a little thinner here to make them more like central force springs, so to minimize to lower bending. But of course, these are not central force springs by any stretch of the imagination. You know, to calculate what they actually are, to do it for the real system would be hard, but it's very robust. So there's the target. Now I'm going to put the strain on at the source. Okay, you see the response at the target. Okay, and I have one right here. If you come to my office, come and visit, you can play with these. We can make 3D ones by 3D printing. And it works as well. Unfortunately, I don't have a movie because I'm such a theorist that when Ingrid Bischofberger, who did this with Nidhi in Sid Nagel's lab, she brought me one, and I broke it within 5 minutes. so I don't have a movie of that, but it works. It worked for those 5 minutes. Of course, we're all interested in multitasking, right? We want to know how many different things can I do at the same time? How many places can my brain direct extra oxygen at the same time? Okay, and in mechanical networks and proteins, this is actually interesting too. Proteins that have more than one allosteric site, okay, are often called moonlighting or multifunctional proteins, okay, and they exist. You can have proteins with 2 or 3 allosteric sites, different sources. It turns out that if you look at this is the probability of being able to satisfy all my constraints. In other words, the probability that I have achieved my goal. Okay, so this is 100 is 100% success. Every single network I start with, I am able to tune it to get what I want. Okay, and that's what's on the y-axis. On the x-axis is the number of targets. So I'm going to start with a fixed number of nodes. Okay, here's n. This is the number of nodes, and I'm going to just ramp up the number of targets. And you can see that for different system sizes, as my system size increase, I can tune more and more targets, and it's huge. Okay, so for a system of 4,000 nodes, right, I can actually successfully tune easily 100 targets. Okay, no problem, either in the flow or the mechanical networks. I'm even more successful in the flow networks. All the results actually collapse onto a single curve. There are interesting power laws here. But the key is it's really easy to do a lot of things. And what we're asking the brain to do, or what we're asking proteins to do when we have 2 or 3 allosteric sites, it is far, far below the maximum number that they could possibly do. Okay, not surprising because it was able to find these solutions by evolution. Okay, so it turns out that the limit of multifunctionality is a constraint satisfaction transition that's very similar to the jamming transition. And this tells you, why is it so easy to tune one function? Why do I always get 100% success, nearly 100% success? It's because, in fact, I could do hundreds of them. That's the maximum number I could do is hundreds. And if I'm just trying to do one, it's really, really easy.
Andrea?
Yeah.
This is Itai. When you think about
Okay.
allostery, so far the things that we've talked about are like continuous deformations. Is there ways to get discontinuous snap-through behaviors? And is that something that can be tuned as well?
Yeah, that's really interesting because what you want to do is you want to have two different basins in your constraint satisfaction landscape, right? You want to be able to snap from one basin to the other basin and back. So, all right, postdoc Jovana Andreevich, who's working with Sid Nagel and me, she's taken, so what she's done so far is she's taken networks that were tuned to have allostery at 0 temperature, and now you apply temperature to it, and they naturally do that. They go bam, 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 bam. They have transitions from one state to another that both satisfy the constraint. It's really interesting. You just take these 0 temperature systems and raise the temperature, and you start seeing that. Okay, and so yeah, we're extremely interested in that. But I don't have a full answer to you yet, whether we can do that by training at non-zero temperature and seeing whether we can really control that process of jumping from one basin to another.
Andrea, I also have a question, Carolina.
Yeah.
You have this, usually, if I don't mistaken, you have two nodes and you open in one side and require two nodes to be closed or to closer in the other side.
Right.
And then you can do this for several nodes, right? You show that you can have more than 100 sites when you do that. But did you try to do something with more nodes or something? Let's say we have 4 or 5 nodes, and you require to do something else in the distant nodes, or it's always
Yes. So we have taken multiple sources. So you can tune multiple sources to multiple targets. And you can do it either as source target pairs. So I want this source to have that target, this source to have that target, et cetera, right? You can tune multiple source target pairs. So Daniel Hexner did that. Or you can tune a cluster of source nodes and a cluster of target.
I see.
So Jason just played around a little bit with that. And you can do it.
Right. Okay. Using the same algorithm that you were explaining here, the same cost function, you reached it.
Yes.
Okay.
Exactly. Using these cost functions. So, so I just want to point out a little thing here, which is really quite fun. This was work done by Miguel Ruiz Garcia, who's a postdoc with Eleni Kadafori and me. Turns out that there is geometrical frustration during this learning process. There can be. So if your target is really close to your source, okay, here this target is red and the source is blue, then there are relatively few bonds that are worth tuning that will really affect what happens at the target. Those are the yellow ones, okay? But if it's far away, there are a lot more bonds that you could choose to tune. And so if you tune the targets far away first, you can mess up the tuning of nearby targets. And then if you fix these up, that can mess up the far away targets. So that can constrain your success in pruning, okay? Limit your success. And what he figured out was, it was sort of cool. You take this idea from protein folding of a funneled landscape. So our usual thing is we want to minimize, we want our target pressure drop at site I, or at target I, to be the desired target pressure drop, right? And here we just put on a step function. We're usually doing an inequality, actually, where we just want it to be bigger than this desired target drop. It doesn't have to be exactly equal. We can make it bigger, okay? Doesn't matter whether we do this. All right. that doesn't change things too much. Now, instead of minimizing that, what he suggested, let's weight it. Let's minimize this, but weighting it according to the distance from the target to the source. So the nearby ones get tuned first, okay? They have a bigger weight in the cost function. They matter more in the cost function. That makes a funnel, okay? And we end up tuning the targets in order of distance from the source. So we do the nearby ones first. The algorithm will just naturally tune the nearby ones first because they're more important in the cost function, okay? And by doing that, we can actually change the scaling of this. And what we find is that in that case, there is no transition in the thermodynamic limit. Okay, it's not sharp. And you can tune many more targets. So actually, for a system of only 1,000 nodes, you can tune about 500 targets successfully.
Sorry, Andrea.
Excuse me?
I have a question, but about the previous problem.
I'm sorry, can't quite understand that.
I have a question, but it's about the previous problem.
Earlier stuff? Yeah, go ahead.
Can I get the opposite problem? I mean, can I protect a certain area of the network of this frustration by using your method?
Can you protect a certain part?
Yeah.
A certain target area?
Yeah.
So that there's no strain?
Yeah.
There. Yes. Yes, you can do that. Absolutely.
Yeah, but what would be the way that can I get?
You specify a target strain of 0 in response to the source.
Ah, okay. I changed the constraint.
Yeah, it works. Yeah, Jason did that.
Okay.
Yeah. Yeah. Yeah, these are great questions because that's actually important for some things. In fact, I'm writing a grant proposal now with somebody in Delft who wants to make these implants, medical implants. Where, you don't want any strain at some spot. You want to protect it. Okay. So I just want to summarize this part, learning functions by gradient descent. It really works. It's extremely successful. It's very easy. And the reason why is because we have a lot more degrees of freedom than we have constraints. Okay, so if we only want allosteric in one place or a few places, and we allow all of the bonds to change, okay, that's a lot of degrees of freedom just to satisfy this one constraint, and we're going to be successful. Okay, and that's the same idea. It's called overparameterization in machine learning. You want to use a huge neural network, much bigger than what you actually need, so that you have a lot of learning degrees of freedom to minimize, so that you can satisfy all of your constraints. And that's where learning is easy. Okay, so that's the same idea. I'm going to now, this is my bullshit line. This brown line is my bullshit line. This is what Sid calls the bullshit line. So Sid has this thing that, okay, up to now, you should believe everything I told you. Everything I told you is based on our findings, okay? Once I descend below the bullshit line, though, you can take it for what it's worth. And so the bullshit speculation, right, is, oh, maybe this is why so many proteins have managed to evolve allosteric. This is why it's so common, because it's really very easy. They have tons of degrees of freedom to do it. And so even evolution, natural selection can get us there. Okay. And why? Why is that? Because tuning one function lies well in the satisfiability state. And okay, there are lots of interesting questions, but let me get on. Okay. There's a problem with this. By doing gradient descent using edge demons or backpropagation or whatever. This works fine on the computer, okay? But it's not scalable. If I really wanted to have a material that I could mold with my hands, okay? with, 10 to the 10 different edges, right? There's just no way I could solve this. So it's not scalable. It requires this precise microscopic knowledge. I need to know the network geometry, the topology, and all the spring constants. I have to know everything. Equilibrium lengths, I have to know all of that. And then I had to be able to go in there with my little edge daemon and make the modification that I want. The gradient descent tells me what to do. So this is not very practical for making real materials. It's fun to make these things like this, but what relevance does this have for the real world? So, and this is a problem for artificial neural networks too. It's that design by minimizing a cost function is inherently a global process. If I want to do it by gradient descent, I have to be able to calculate the cost function. I have to calculate its gradient, and I have to be able to take a step down that gradient. And these are global steps, and they require a processor and memory. Okay, and so that's a problem. So the question is, can materials learn how to function without a processor? And here now we're going to let me draw the contrast between an artificial neural network and a real one. Okay, the artificial neural network needs a processor, right? As I just said. The real one, there's no computer attached to our brains. Our brains do it on their own. Okay, they don't need a processor. In the artificial neural network, the learning is concentrated in the processor, whereas in the brain, the learning is distributed among all the neurons. And all the neurons learn according to local rules. So the advantage of being distributed is that it's incredibly robust to damage. You can actually, some people have to have half of their brains removed because of very severe epilepsy. They can still function. Okay, they can still lead normal lives. So even without half the brain, you can survive. If you did any damage to the processor, you can't learn a thing. Finally, these require huge amounts of power, whereas the brain, requires very little power. Okay. In fact, it turns out Google uses 0.3% of the world's power consumption. So can materials learn more like the brain? So here now, we take advantage of, not initially really understanding what we were doing. So when Carl Goodrich did the first thing on tuning by pruning, he didn't actually remove the bonds that changed the bulk modulus the most to get negative Poisson ratio. That understanding came later with Daniel Hexner, who's an amazing postdoc who's at Nagel and me, who's now at Technion. Carl is now at IST Austria in Vienna. So the idea was, what he did was he pruned the bonds that made the biggest contribution to the bulk modulus. And those happen to be bonds that if I put the system under isotropic compression or expansion, doesn't matter which, if I put them under a small infinitesimal compression or expansion, the ones that would be under the most stress, okay, which would be the one that he pruned, okay, would be the same as the one that makes the biggest contribution to the bulk modulus, okay? So we got a very similar result. Really easy to take the Poisson ratio to -1, okay, by pruning the bonds that were under the greatest stress. So we realized, okay, if we have a system where bonds break above some threshold stress, okay, so just have bonds that break. If the stress gets too high, they start breaking. Now I apply isotropic stress. The ones that are going to break first are the ones that change the bulk modulus the most. Bam, I'm going to just tune myself to have a negative Poisson ratio. Okay? That's scalable. I didn't need to know anything to do it, okay? So if we go back to this formulation of two cost functions and two sets of degrees of freedom and needing to minimize two of them, okay? If I think about minimizing this one, the forward calculation, minimizing the physical cost function, yeah, on the computer, that's time consuming, that's hard, okay? Takes work. We know how to do it, but you know, that takes computation. But in the lab, physics does it for you for free. You don't have to worry about moving the node positions to adjust the system so that it minimizes elastic energy. The network will do it all by itself. Okay? So in the lab, physics does the forward calculation for free. Okay? But I saw this back propagation, but the idea now is that the back propagation will be replaced by this process where instead of calculating anything, I'm just going to put the system under isotropic stress. Okay, and then I'm going to prune the bonds. It's almost the same as pruning the bonds that change the bulk modulus the most. It's pruning the bonds that make the biggest contribution to the bulk modulus. And it works. So what does that mean? That means that the learning cost function must be sort of similar to the elastic energy, because that's the only thing that this system knows how to minimize is the physical cost function. So the learning cost function must be similar to the physics cost function with the right boundary condition, which in this case is isotropic strain. And in that case, each bond is just going to respond according to stress on it. It's going to, do I break or do I not break? Okay. And it's going to do it without knowing, it doesn't need to know what the other bonds are doing. So it's not a global thing. It's a local rule. Is that clear? I want to make sure that's really clear.
Yes, I think.
So that's the idea of directed aging. Okay. So here's our elastic energy. And I'm just going to make my learning cost function what I'm going to call the clamped energy. What do I mean by that? So if I want a negative Poisson ratio, if I apply a source strain squeezing like this, I want the system to shrink like this by the same amount. I want the target strain, I can call that the target strain, to be the same as the source strain. Okay? So what do? I apply both the source and the desired target. Okay? That's the clamped condition. Both the source and the desired target response. Okay? And then I do gradient descent, and let's just look at it, right? Here's my elastic energy, just springs, central force springs. I minimize this respect, for example, to the equilibrium length. Okay? And when I do that, right, every term drops out except the spring that I'm looking at, so that I just adjust the spring to minimize the tension on the spring. If the string is getting stretched, okay, I just let the equilibrium length grow. If the if it's being compressed, I just let the equilibrium length shrink. Okay? And that works. Okay? All right. So that's the idea. It works. Here it is. This is a picture of a system that's in the lab. And sadly, I was looking around this morning just before starting, and I realized I left the sample at home because I was giving Zoom talks at home for so long. So what Needy did was she laser cut just a network like this from a solid foam. Okay. Then she just took it and she compressed it isotropically. She just took this square thing and she put it in a square box that was too small, forced it in there, okay, heated it up, waited a little while, took it out, and it had a negative Poisson ratio. Okay, and this just shows that depending on the target strain, depending how small that box was that she aged it in, okay, she was able to change the Poisson ratio, how negative the Poisson ratio actually got. Okay, this one is the blue diamonds. Okay, and you can do this in an oscillatory fashion. That actually works even better, Danielle found. That what I do is I just put on an oscillatory isotropic strain. Compress, expand, compress, expand, compress, expand, and I let directed aging go the whole time, let the equilibrium lengths adjust to this. When you do that, you actually carve out a valley in the energy landscape. And that works. And he can tune Poisson ratio this way. How am I doing on time? Okay, we're gonna not dwell on the memory. Okay, I just had to tell you the memory aspect because it's so cool. So this is after no aging, no cycles. This is the number of cycles of aging that you do. And you see that you get to this point where the Poisson ratio is really close to -1. Okay. The cool thing is, if you look at what you get in the end, okay, you can see it's -1 over some range. And the dashed lines are the range over which the system was trained. In other words, for the red system, he went between -5% and 5% strain. Okay? And in the end, just by measuring the Poisson ratio, you can read out the strain at which the system was trained. It remembers. There's a memory of the strain at which it was trained. Okay? That you can just read out from the finished product.
Sorry, Andrea.
Different training strains. Yeah.
I have two questions. One is, can you explain again why are you calling this aging? And again, in which sense do you interpret this as memory, what you are now showing us?
Yeah, so why am I calling it aging? I didn't explain that. Thank you. This is made, this system is made out of solid foam, and it actually changes. So it's the regions, we don't know what's happening. This is a really complicated system. I guess you could do it probably with finite element and really figure out what's going on. This is not a spring network by any stretch of the imagination, right? But what is still true is that the regions that are under higher stress are deforming plastically, and they're deforming faster than the ones that are under lower stress. So that's what we call, that's the aging process, is this plastic deformation that's occurring. And we're directing it, we call it directed aging because we're directing it by applying the boundary condition that we want to get the desired result. In other words, you give me what you want, okay? Negative Poisson ratio, I tell you, okay, you want this clamp boundary condition. I know what the clamp boundary condition is. I just apply the source and the desired target. That's the boundary condition. And I can I direct the aging process under that stress, okay? I apply the right stress and I direct that aging process to get the result that I want. So that's why we call it directed aging.
Okay, you're right. Okay, understood.
Yeah, I didn't explain this thing because this is not the central force spring network at all. It's a real system. Yeah. So we can do it on the computer or we can do it in the real system, but it does actually work. And this is just an example of allostery under the driving strain. So this is the source bond and this is the target bond, and he lets it evolve, the equilibrium lengths evolve according to the stresses on them. And so there's a readout. So the green is the strain at the source. The red is the readout strain at the target. And what you see is that it's going up and up as you train it, and it eventually reaches 1. Okay, the strain at the target after many cycles eventually reaches the desired target strain of 1. So you get allostery. So that's great, except that it doesn't always
Andrea,
work.
is it a type of not elastic behavior? Would you call this like this? A plastic behavior?
Is this really plastic behavior?
Yeah, the one that has just shown the fact
so
that
it's at least partially plastic, so that when we let the system, we age it, and Needy ages these things in the thing, and then you can take it out, and even a week later, if you pull on it, it's still negative Poisson ratio. It's not as good as it was initially. So some of it is actually just is a viscoelastic response, but a lot of it is actually plastic.
Okay, it's interesting actually to obtain that with this procedure, right? It's interesting that you see this type of behavior with this procedure.
Yeah.
Just a comment.
Yeah. Yeah, we were really, I cannot tell you how we were delighted we were when it actually worked. We weren't sure if it would or not. So it did work in that case that I told you, but it requires coupling between the source and the target. And it turns out that we now understand the near isostaticity, that's fine. There's a long length scale that diverges at isostaticity. And so you get this coupling, and so it works. But if you're not near isostaticity, it's a problem. And in fact, I asked Naki to do this in flow networks when he first arrived as a postdoc. He couldn't get it to work. And he realized that the problem was that the learning cost function isn't really the energy of the clamp state. That's not the learning cost function. We're not minimizing the right thing. So how can we do something that really reliably works, that really minimizes the learning cost function and not something that's only approximately equal to it in certain cases? So to do this, he borrowed from ideas of contrastive learning. Okay. And it turned out it was like equilibrium propagation. We didn't realize it at the time. That's the thing in machine learning. Very similar to what was already there. So here you compare two cases. The free case, which is what you want. You want to just apply the source, not do anything at the target, and you want to get the right answer, right? But of course, when you start out, when you apply the source, you don't get the right answer at the target. Okay, but that's the free condition. And then there's the condition where you apply the source and then you apply the desired target response to. Okay, that's what I just showed you with directed aging. So this is ingenious, okay? Because the original cost function, right, was the desired response minus the free response, right? I want the free response to be the desired, the response when I just apply the source. I want the response to the target to be the same as my desired response. That's my original cost function. And I have to square it to minimize it because this could be positive or negative. But our new cost function, okay, we're going to take the energy of the clamp state minus the energy of the free state. And this is where physics is essential, because physics tells me that if I apply the clamp state, the energy has to be higher. That if I let the target do what it wants, the energy is lower than if I clamp the target away from what it wants. That has to raise the energy. Okay, so that means this is already greater than or equal to 0 just due to physics. I don't need to square it. It's linear. And it's that linearity that when I differentiate it, do gradient descent, for example, on the equilibrium lengths, my rule for changing the equilibrium length of bond J, sorry, I keep forgetting to correct that. These should be J's, okay? Just depends on the tensions on bond J. But I need to compare the tension in the clamp state to the tension in the free state. Okay? So that's it. I've got a local rule. All I have to do is compare the tension in the clamp state to tension on myself in the free state, and then I adjust myself, okay, accordingly. And that will be equivalent to gradient descent on the cost function. It is gradient descent. Okay. And the same works for power. So this is in the language of an electrical network. Here's the power dissipated in the clamp state minus power dissipated in the free state. That I do gradient descent on the conductances. And now the change of conductance of edge J just depends on the voltage on edge J in the clamped and the free states. Okay. So this works, okay, on the computer. So Naki did the MNIST data set, the classification of handwritten digits, zeros and ones, just zeros and ones. So I corrected it a different talk. Principal, P-A-L, not P-L-E. So my input nodes are the top 5 principal components of the image. So we're cheating a little bit by doing principal components, but we do the top 25. So I have 25 nodes that feed in voltages according to the principal values of the principal components. And then I have 2 output nodes. I have a 0 node and I have a 1 node. Okay. So when I feed it a 0, the 1 node has a large voltage and the 0 node has a small one. When I feed it a 1 node, okay, the 0 node has a small voltage and the 1 node has a large voltage. So it classifies these images. And it does it with an accuracy which is comparable to simple machine learning algorithms, about 97%. Okay. But, right, that was on the computer. We can't really avoid global gradient descent. We still had to minimize the physical cost function in that case. We had local rules to replace back propagation, but we still had to minimize. So for the learning cost function, we had local rules for Naki's calculation that I just showed you, but he still had to minimize the physical cost function on the computer, right? And really, ideally, you want to do this in the lab so that you get that for free. Okay, so what we want to do is we want to implement local rules, right? These coupled learning so that we don't need a processor for back propagation, but to really avoid a processor entirely, we need to do this in the lab. So this is where Doug and Sam come in. And this was ingenious. Okay, so you can easily buy digital variable resistors, no problem. Okay, that have 128 different resistance values. But for coupled learning, I had to be able to compare the voltage or the power across the resistor I and edge I. I had to compare it in the free and the clamp states, right? But the free and the clamp states correspond to 2 different boundary conditions, and you cannot apply 2 different boundary conditions at the same time. So how can you possibly compare it, okay, without using any memory or a processor? On the computer, we just stick them in memory. Naki just sticks it in memory, and then he compares it. He does the difference, right? And the processor does it. But we want to do this without a memory or processor. So this is Doug came up with that. Something I think is, I just found it very clever, which is to build 2 identical networks, twin networks, where each edge always has the same resistance. One runs the free boundary conditions, the other one runs the clamp boundary conditions. And so each edge in our network is actually 2 edges, one running free and one running clamped, okay? And then they are connected together through circuitry, which implement a modified coupling rule in this case, where we just adjust the variable resistor up or down, okay, just according to the sign of the voltage squared across the clamped minus voltage squared in the free case. So it just has circuitry that does that. So each edge is this little circuit, okay? And then we update the resistances of both the free and the clamp twin, right? So that they always have the same resistance. And this works. We can classify the iris data set. Okay, so this is, you give the 4 different measurements of the iris. Okay, that's 4 different voltages. okay? And there are 150 different sets of these measurements, and there are 50 each of 3 different kinds of irises, okay? So that's 3 different target nodes. So 3 target nodes, 4 input nodes plus ground, okay? And starts with a high classification error, and you let it go, and bam, it learns it. It classifies it. And a classification accuracy about 97%, comparable to linear classifiers. It really does work. And the reason why it works is because all you're doing is it's always the same learning rule. It's always the same way that you adjust the resistance. What changes for different tasks is you just change the boundary conditions. You just change the voltages that you apply to inputs and outputs. Okay? So here's the same network. First it learned allostery, and then said, I'm sorry, classification of the irises. Okay, here's the classification error went down. And then Sam said, no, learn allostery. So here's my ground node. I want you to, and I apply an input here, and I want a desired output there. Okay. Initially, here's the mean squared error. Initially, it was high, but after training, it dropped. It learned it. Then he said, no, do this. 1 input. Oh, sorry, that's ground. 1 input, 2 targets. 2 target voltages. Learned that. Okay. 2 inputs, 3 targets. No problem. Okay. 1 input, 4 targets. No problem. Learned it. Okay. Each time the error is dropping. This is the scale. And then he said, learn 2 equations, learn how to solve 2 equations for 2 unknowns. Linear regression. So I did that. Different set of 2 equations and 2 unknowns. Did that. Now go back and learn allostery again, this case. It learned it again, but interestingly, the resistance values once it had learned it were not the same as when it learned it the first time, because I started out with a different initial condition. So there are many, many different solutions. The system is large enough so that it reaches the global minimum, but it can find many different solutions that satisfy this. Okay. So it really does work. All right. And it's robust to damage because learning is distributed among the edges. It's like the brain. Okay, each edge is learning on its own, which means that if I rip out an edge, I can still learn. So here's a case, here's a network that learned with the whole network intact. And then Sam went in and ripped out this edge. Errors shot up, okay? But then it learned it again. Now rip out that edge, learned it again. Rip out the purple edge. Interesting, that did nothing. In fact, Sam found that he had to choose pretty carefully. That most of the edges, if he removed them, it didn't even increase the error. He didn't have to even retrain, okay? But some of them, like the green one, he really did have to retrain. In the end, he removed 1/3 of the network, and it still was able to learn. Okay, so it's really robust to damage. As long as the network is big enough so that I have enough learning degrees of freedom with respect to my constraints, I can damage them, and it's no problem. And that's hugely important. You need to be able, if I imagine manufacturing this thing, it has to be robust to manufacturing error, which many chips are not. Many of these learning chips, the neuromorphic sort of things, are not robust at all. This is incredibly robust. Okay, so why are we excited about this? Oh, here's our 2nd generation analog version. This is, oh, geez, Mark Miskin's name should be on this. This Mark Miskin, Itai knows, he's brilliant. We went to him with this, and he came up with a way to do it. Okay, different design, not using the variable resistors, different design, it's using transistors. So now we have an analog version. Here's our network. Okay, it's slightly nonlinear, or it's somewhat nonlinear. It depends on the voltage. So different gate voltages. So we can actually solve XOR with this now. We're not constrained to just linear classification. We can do nonlinear as well. And the most amazing thing is that the second generation system is 5 orders of magnitude faster than the first one. Okay, so this is just what Mark has now. It's a massively scalable design. This forward problem, the forward computation of minimizing the physical degrees of freedom just depends on the overall capacitance of the system and the size. It's nanoseconds, okay? The circuitry replaces back propagation. It solves a local problem. It now does it in 10 to the minus 5 seconds. So that our second generation breadboard implementation, this thing, okay, it's tiny, okay, but it already outperforms the computer version. It's already faster than we can do it on the computer. And we can send this to a foundry. So in January, Mark's going to have a postdoc who can turn this into design for a foundry. Okay, so we'll send it out. So, and we expect that, when we do that, it's not going to be hard to scale up the networks by up to 6 orders of magnitude. That's all standard. Okay, while decreasing the total footprint. Our current network is very big. Oh, I have a picture. Where do I have a picture? No, I didn't put it in here. This thing is very big. Okay, but we can have it on a chip. It'll be much smaller. It'll be on a chip, and we think we can get even another order of magnitude out or 2 out of the circuitry. Sam has already speeded up the time for each training example to be shown to be milliseconds, and it only consumes, of order 1 watt of power. I'm going to skip all this stuff. It's sort of fun. It just shows that when we make our system even more like the brain, just taking inspiration from the brain, it does even better. The brain really knows what it's doing. But I just want to say that, nowadays for sustainability, minimizing power consumption during learning is a really important thing. And already by avoiding the use of a processor and memory, okay, they consume much, much less power. But we can lower it even further, okay, by adding a term to the learning cost function that just wants to minimize the power in the free state. Okay, so this is the learning cost function. This is the power regularization term. And by adding this little term, basically there's a trade-off. The more we lower the power, the higher the error will be. But there's no point in having the error be any lower than what you get from the noise in the circuitry. So we can actually put on quite a large regularization term and without impacting the error at all, okay? And we can save, we estimate up to an order of magnitude or 2 in the power by doing that, even beyond what we have already. Okay, so that's it. That's the story. So there's this idea of gradient descent on, 2 learning cost functions, 2 cost functions, 2 sets of degrees of freedom. You can either do gradient descent on both. That works fine for inverse design on the computer. If you want to do in real life, scalably, you need to have local rules. And we now have this coupled learning. It's a systematic framework for how do you write down the local rules for what you want for different design problems. So we're excited about that. That's it.
Okay, thank you very much. Are there questions for Andrea?
I was curious, Andrea, about the robustness against damage that you mentioned. Are you...
Carolina, somehow I can't hear you very clearly.
Okay, so if I speak like this, can you hear me?
That's a little better, yeah.
Concerning the robustness against the damage that you commented, did you try to see, for example, how how many damages you are able to do in order to keep the learning, you know, the system. I imagine that above a certain damage, it's not going to work anymore, and this is related to the brain.
In this case, he removed 5 out of 16 edges.
5
and
out
he
of
could still
16.
do it.
Okay.
Once he tried to do 6, he couldn't do it.
So it's about 10%? Is it right?
About a third.
About
1/3.
a third. Okay, okay. And it's still working. So it seems that if it
Yeah,
finds...
and this was, but it depends on the size of the network and the task.
Okay, okay, okay. I see. So the system finds other routes to do the task. Okay,
Exactly.
that's very interesting. Okay.
Exactly, because as long as you're far enough below the constraint satisfaction transition, right, you can find many different routes.
Yeah,
And
yeah.
so by this damage is basically ripping out degrees of freedom. It's decreasing the number of degrees of freedom. And so there's some point where you pass the constraint satisfaction transition and you can't do it anymore. But as long as you're not close to that, then you can rip out all of these and it makes no difference.
Yeah, that's quite interesting. Okay. Other questions?
Okay, Andrea, are you going to stay here for a few minutes so that people can come down
I have
to
until, what's my calendar?
if someone wishes to ask
I have
questions.
until 10:30. Yeah, I have until 10:30.
Okay.
Andrea, thanks a lot for
Thanks a lot.
the 3 lectures that was very, very interesting. And so let's thank Andrea again.